Good morning. This is the third lecture now on force convection, and today we will begin by looking at solving a few problem on force convection heat transfer. We will then move on to examine what are the integral equations of the boundary layer. We had derived yesterday the differential equations. Now we will look at the integral equations. Then we will look at heat transfer over a cylinder and a sphere. What are the main features of this? And finally, we'll end up by looking at internal flow. So this will complete the basic problems, the type of problems that one encounters in force convection. Before that, we have had some questions that I will take up now. There was a question yesterday that is heat transfer in forced and natural convection the same? Okay, the fact is that forced convection produces a very different type of fluid dynamics than natural convection does. And in general, heat transfer coefficient in forced convection are much greater than those in natural convection. So it's not the same, and this can cause major issues. For instance, if you look at computers that were made 15-20 years ago, the cooling of the chips was done predominantly with natural convection, with just a heat sink sitting inside the cabinet. These days, practically every chip has a fan on it, which is why we have gone into forced convection. When we solve a few problems, you'll see that a plate in air, even with a very mild velocity of a few meters per second, will have a certain heat transfer coefficient, something like about, say, 10, 100, 50, in that range, 50 to 100 watts per meter square per Kelvin. In natural convection, a plate or a cylinder would have like 3, 5, 6 watts per meter square Kelvin. So there's almost a 10-fold increase in heat transfer coefficient with forced convection as compared to natural convection. And when we come back to next week, we will see how natural convection is and why it is that it is so low. Then there's a question that explain about the wake region. So this came out yesterday when we were looking at the plate, and we were only worried at the time being that if the flow is coming here, it forms the boundary layer, and the boundary layer grows until the edge of the plate. Then the plate is gone, but the fluid continues to move. What does it do? So I'll very quickly tell you a few basic things, and we will see some more videos today when we look at cylinders in cross flow. Take the velocity profile at this plane. This is the edge of the boundary layer, so the velocity outside this is going to be uniform. This is same as the incoming velocity u infinity. But here, because of no slip condition, at this point it has to be 0, and so there will be a profile which comes like that, and a profile here that is like this. So the velocities here will be decreasing, and this flow continues behind this if there's a big domain there. Now what happens to this velocity profile is what we would see as you go back here. That this 0 thing, this point which at 2 velocity, will take a finite velocity because the other fluid layers are moving around it. This deceleration that was felt up to this point will be felt a little beyond this point. So at this location, say u infinity will come to this point. Similarly here, instead of here, it will be here, and the center line velocity will have increased. So now you have velocity which is uniform outside this, and in this we end up getting a velocity profile like this. So this continues for a very long time until finally it becomes straight. This is a very simple behavior of the wake, and what it tells us is that the region where you have this happening, this keeps on increasing. This is the edge of this, so this keeps on going. The wake effect, the size where the velocity of the plate is felt, that increases as you go downstream. So here also this is happening, and the center line velocity, which was 0 at this point, slowly recovers, and far away from the plate, you get almost, say this was the plane that you're looking at, you'll get something like that. A small velocity deficit, the deficit keeps decreasing, and the wake keeps spreading, and it takes quite a bit of long distance before this profile will become completely uniform. So this is in itself a challenging problem, although there is no surface coming in here. The fluid mechanics of this is quite important. And we'll see that when we look at cylinders, what happens. This is also a big issue when it comes to the weight of a vehicle or an automobile or an aircraft. We have to worry about these parts. Okay, so this is what happens in a wake. The mathematics of this can be worked out. The third question was, how is ideal fluid convection different from real fluid? I guess that when it says that it is ideal fluid, it means that this is a fluid with no viscosity. So this would be like what we talk of in potential flow, that viscosity is zero. Once that is the case, then if you look at this plate, everywhere on this plate at any place, the velocity will always be the same everywhere. The result is that an observer moving with this fluid will not see any relative motion of the fluid, and although convection is taking place, that this element is moving, it is also getting conduction here and passing conduction over there. So this is what is called then a slug flow, and essentially this is what you get in case Prandtl number is very much less than 1, where conduction is so important. Velocity profiles are nearly uniform, not really nearly exactly uniform, but it starts to behave like an ideal fluid. And then you have what is called a plug flow. Thermal boundary layers will develop similarly, but heat transfer will be hugely dependent on the conduction effect. In a real fluid, which is a viscous fluid, we have the boundary layers growing in. The boundary layer becomes like a barrier between this fluid and the plate, so heat transfer coefficients go down. Ideal fluid, there is no boundary layer, in which case it means that the fluid here and here is they are on the plate, they are very close to one another. So you expect qualitatively that heat transfer coefficients in this case will be much larger than the case where there is a real fluid which has a boundary layer. So that's the qualitative way of looking at ideal fluid versus a real fluid. So essentially what we are saying is that boundary layers are in the real world unavoidable. They will always be there. We have to do the best we can to understand and do the engineering in such a way so that the objectives are met with the least possible problems. And that's what makes both fluid mechanics and convection heat transfer so challenging. So those were the questions. Now I'll come to solving or giving the solution process of a simple problem. So here is what I've set up the problem, that you have a flat plate of length L width W, which is aligned with a flow coming on it at uniform velocity U infinity and T infinity, temperature T infinity. This plate is kept at a constant temperature, and we want to calculate the heat transfer rate from this plate. That's the problem. So first we pose what is the problem that is given, and we develop our own terms and symbols. That plate length in the direction of the flow is 2 meters, width is 1 meter. Incoming fluid, let's say that the fluid that's coming on is air, so that is the fluid. Velocity is 10 meters per second. The temperature of this air is 20 degrees Celsius, and the wall temperature is 60 degrees Celsius. These are the numbers I am just taking for example. And the question posed is, what is this? Q dot W, which is the heat transfer rate from the whole plate or the wall. So we first say, look, let's decide what is the geometry. The geometry will tell us what approach to take. So we say that this is a plate which is flat and smooth. So we say this is smooth flat plate. The problem didn't say it, but we say, okay, we are going to assume it to be that way. And we say that it is aligned with the flow, so that L is in the direction of the flow. So this is the geometry part of it. Then we say, well, what is the free stream condition here? We say it is laminar flow. It has got no turbulence in it. So this is the flow. And we say that when the flow comes onto the plate, this edge is very sharp and clear. So what you are saying is that at the edge of this plate, everything is perfect and a laminar boundary layer begins to build from there. Okay, so this is what we have done. Now, just to give you an example that what I said that this is a very idealized situation, let's look at some cases where pose such a problem, but the practical issues are very different. If somebody would ask us that what is the heat transfer rate from the top of a bus? So this is the top of the bus. It is moving in air. What is the heat transfer rate from the bus? The bus could be air conditioned, or we could say that it is getting heated by radiation. So what is the rate at which it is cooling? Something like that. Or somebody could say, no, what is the heat transfer rate from the side of a building on which wind is coming? Or another example could be that a tray of food is kept on a table or somewhere and air is blown on it. What is the rate at which the food is being cooled? Or say a pool of water on which air is blowing and we say what is the rate at which it is cooling the water. Now these are practical situations. And you can see that strictly speaking, none of them would qualify to that idealization that we are working with. But here is what we have to do. We say, look, as a very first approximation, the simplest way that I can get any answer for any of these problems is that I will assume that the roof of this bus is like a flat plate. It is moving, so I'll say air is coming onto it. And for the time, in reality, if you have a vehicle like this and air is coming on it, the streamlines will go like this. So the flow on this is not strictly flow over a flat plate, but we'll say to begin with, I will ignore that and assume this to be a flat plate on which this air is coming, and now I'll calculate the heat transfer. Similarly, we do the same thing for the building, with the roof or the side, and say that air is coming on top of this. We ignore these things and say, look, at the first cut, I will take this to be a flat plate on which air is coming. I will get an answer. It won't be exact answer, but I know that it is the order of magnitude of the answer that is of concern to me. Is it 5 kilowatts, 10 kilowatts, 100 kilowatts, 0.1 kilowatt? That number I will at least get a feel for it. It's not the exact answer. Same thing with food. It could be kept on a table on which it is moving, and this is what happens in mass manufacturing, that after food is cooked, it goes into a tunnel where it is cooled, or it's kept in a cabinet where it is cooled and then packaged or whatever is done. And we can say that, look, food is slightly rough here, so if I can get heat transfer coefficient for a rough surface, I will use that. That's a little better. But okay, if I don't have it, my simplest first cut analysis is to assume this to be a flat plate and assume the food to be at a certain temperature and see what is the heat transfer rate. So that's how we take a practical problem and reduce it to the simplest possible case, and that is always the nice thing to do whenever you solve even a complicated problem. If tomorrow you want to do a computational fluid dynamics or a computational heat transfer solution of this problem, it is good to do this simple analysis so you know where the answer is likely to come from. What is the order of magnitude? So if your simulation is giving you something very different, you know there's something to worry about. I need to go back and read it. So we have now posed the problem. We have got all the parameters we want, and now we start and say, well, how am I going to approach this problem? And we say, look, I know that Q dot this thing is to be equated with the average heat transfer coefficient for the plate multiplied by the area of the plate, which is L into W into a temperature difference, TW minus T infinity. Now the problem is, how do I get the average heat transfer coefficient for this? And for that, we say that we'll first see what type of flow do we have on this. And for that, we said air, your Prandtl number is 0.7. You can look up the tables. And if you want the exact value of Prandtl number, we'll come to that in a minute. And we said for Prandtl number 0.7, the hydrodynamic boundary layer, if it was like that, the thermal boundary layer will be almost like about the same size as the hydrodynamic boundary layer. So this is half the story we know now. They will both grow together. That is the second thing, because the flow coming here is very smooth and the entire plate is heated up. The question is, what type of boundary layer is it? Is the whole plate going to have a laminar boundary layer, or will it have laminar and then it will become transition and become a turbulent boundary layer? That's the next question we want to ask. And for that, we need the Reynolds number, where at the end of the plate, which is REL. And to do that, we now make one difference from what we have done in classical fluid mechanics, is that in the boundary layer, since we mentioned that the temperatures are in between T infinity and TW, what is the temperature at which property should be evaluated? And that's the important thing, for which we call this T film. A film is basically saying that it is this boundary layer region that we are calling it, or we say this is T prop or T property, which is what is the temperature at which we should calculate all the properties for solving this problem. Now this is a very important. The reason is there is T infinity over there and T wall over here, which could be very large. In that case, property variations will be quite large. For example, for water between 20 and 60 degrees Celsius, there is a very large change in its kinematic viscosity. The thermal conductivity doesn't change that much, but viscosity is very, very strongly temperature dependent. And this is what causes difficulty in the analysis. So we say, in this particular case, we will evaluate properties at the mean of the wall and free stream temperature, half Tw minus T plus T infinity, which is 40 degrees Celsius. And then we take this temperature, go to the property tables, and we get the value of kinematic viscosity, which is so many meters per second, whatever the value that comes there. We now have this. We go to the definition of Reynolds number. U infinity is known to us, L is known to us, mu we have got from here, and we now get Reynolds number. Based on that Reynolds number, we now make a decision, what type of a boundary layer do I have? So that will tell us either it is only a laminar boundary layer and both hydrodynamic and thermal boundary layers are growing together, or it's a laminar plus turbulent boundary layer and both are again growing together. So we can draw the full boundary layers now, and what we had earlier in this picture we can say that, and let's say for argument's sake that we have the Reynolds number at this point as comes out, say 10 to the power 6, and we know that at 5 into 10 to the power 5 you can approximately expect a transition. It is not an exact thing, but to say, okay, let's say that less than this there's a laminar boundary layer, greater than this you have a turbulent boundary layer. So we can say this and say that the hydrodynamic boundary layer will grow like this, a laminar, and then it will grow as a turbulent boundary layer. So this part could be turbulent. If our calculation shows that Reynolds number is 10 to the power 4, then the entire boundary layer will be a laminar boundary layer. The next thing is what happens to the thermal boundary layer. In the case of laminar boundary layers, both will grow together. In the case of thermal, this thermal boundary layer will now start becoming almost exactly same as the hydrodynamic boundary layer because of mixing taking place there, the fluid going mixed up. Wherever mixing is there, means the hydrodynamic boundary layer is there, and because mixing is there, the temperature equalization is there. So the two boundary layers will be very close to one another once the turbulent flow sets in. So this is what we now know about the problem, that either we have a full laminar boundary layer or a laminar plus turbulent boundary layer, and that tells us which correlation to use. That's the important thing, that we say that if it is only laminar boundary layer, we look up that book or the table or the correlations that are there. I am making sheets which will help you look at it up very quickly and pass that on the website. You can then take that from there and say, look, if it is only laminar boundary layer, what is the correlation I have? And it will be something times Reynolds number L to the power something, Prandtl number to some other power. Or if I have a laminar plus turbulent boundary layer, and with transition happening at 5 into 10 to the power 5, you get some other similar type of a relation for the average Nusselt number. Having done that, we now know in this expression Reynolds number is known, Prandtl number we get from the property table at the property temperature 40 degrees Celsius. Substitute in this equation or this equation, whichever is applicable, and we get the average Nusselt number for the plate. Nu 0 to L means for the entire length, bar means this is the average Nusselt number. This is equal to the average heat transfer coefficient over the plate multiplied by the length divided by thermal conductivity of the fluid. We go back to the property tables, and property tables I mean this is the transport properties of the fluid. At 40 degrees Celsius, we ask what is the thermal conductivity, we get that value, come back here and say that the average heat transfer coefficient is average Nusselt number into K by L. This we have got, K we got from the table, L is given in the problem, and we get the average value of heat transfer coefficient. So now this is known, and then we go to the last step where we say that Q dot W is the average heat transfer coefficient multiplied by the area of the plate L into W, TW minus T infinity. This is known, this is known, this is given, this is given, this we have calculated, the answer comes, and we can say this is so many watts. So that's the way we would solve a typical heat transfer problem. What are the variants of this problem that we could expect? There are so many parameters that we had selected a certain set of parameters. They could all be different. L and length of the plate, that could vary. Width of the plate does not affect the hydrodynamic boundary layer or the average heat transfer coefficient as such, but the total parameter is affected. T infinity could be different, U infinity, TW, all these things could be different. In one case, we did the problem for 10 meters per second. You know, say, well, what will happen if it is 100 meters per second? What will happen if T infinity is 25 degrees Celsius instead of 60 degrees Celsius? Like that. Another variability that could come into this problem is the different fluid that is being considered. We looked at the problem for air. We could have done the same problem for nitrogen or water or sodium or say even engine oil. So these are so many things coming in. Here Prandtl number is slightly greater than 1. Prandtl number is very much less than 1. Prandtl number is very much greater than 1. We have to keep that in mind while picking up that Nusselt number correlation. That's the important thing. So many more possibilities are there. Then the problem could be posed in a slightly different way. You said that, look, the heat transfer rate from the wall is this many kilowatts, air temperature is this much, what will be the plate temperature? Now this problem becomes a little tricky than what we have just seen, because to calculate properties of the fluid, we need the wall temperature. In this case, that is an unknown. So we will have to do a quick analysis, assume a certain value of TW, calculate properties at that temperature, and then solve the problem and see how well the final answer matches with this. Or else, you then go back and iterate and see what the wall temperature is. So from here, we get an assumed value of T film. From here, we get the property, and from there, we solve the problem. So this type of a problem necessarily involves an iterative process. Yet another problem that could be there would be like a designer says, I want this much heat to be dissipated, plate temperature should be this much, and the air temperature is this much. What should be the size of the plate that I need to have? And now we have a lot of possibilities coming in. We have any combination of L and W that is possible. We could reduce L, make W long, and we know that as L increases, the average heat transfer coefficient decreases. Because we are adding bigger and bigger portions where the boundary layer is thicker and thicker, so the average heat transfer coefficient comes down. Our objective would be, keep L as small as possible so that H goes up, and then maybe W will increase. So there will be some sort of a compromise that will come up, and finally we will say, okay, there are so many LW combinations that will do this job. Any one of them can be used for this. So that's the type of issue that designers face, and finally you have to make a decision based on what this LW combination actually comes up. So it tells you that what was like a very, very simple problem that I just showed can actually become any of these type of problems, and it could have lots of implications there. So this is one example, and there can be many more. Constant heat flux wall, there's another case, and the whole thing follows from there. So we will leave it at that, and the idea that this is the general way by which one should solve a problem. It is important that you write down the steps very clearly at each and every point, clearly write down what assumptions you are taking, and then if invariably you will have to iterate, or invariably you have to go back and look at another set of parameters when you're doing real engineering. One calculation will never get the answer. So if the process is very clearly laid out, one can even write the program or write in a spreadsheet, or even manually you can do these calculations. Another variable that could be there, which is worth mentioning, is that we assume that the edge of the fluid coming onto the plate is laminar. It has no turbulence. In reality, that may not be the case, whether it is the bus or the building that we saw, and air that is flowing around us has some turbulence. If that is the case, the problem takes a very different flavor, because if the free stream has some turbulence in it, some variability u prime, then the boundary layer right from the beginning will grow as a turbulent boundary layer, and there will be no laminar boundary layer at all. So now we will get a very different, we will have to go back and look at another set of correlations for only a turbulent boundary layer growing up and use that in the problem. Same will be the case even if it is a flow with no turbulence, and the front edge is jagged or it has got some obstruction there, then also the boundary layer that will grow will right from the beginning be a turbulent boundary layer. In reality, almost always, like all the examples I cited, this is what we are actually going to see. Okay, so many variations of the same very simple, straightforward problem that we thought we could do. Yeah, you solve more problems, and I will also pass on the ideal solutions as I expect on the web, and you can then follow that and critique those things also. So we'll leave that, and we now move on to looking at the integral equations of the boundary. This is different from what we learned previously, which were the differential equations of the boundary layer. There we took an element, found out what all are the mass, momentum and energy inflows and outflows, what are the forces acting on it, and then using the laws of second law of motion and the first law of thermodynamics and the conservation of mass, we wrote the conservation equations. Those are good because when you do a computational solution of a problem, that is what you do. When you go back and the analytical equation, you again break it up into discrete points and then solve the differential equation using various numerical techniques. So that is important for all type of computational issues. The integral equations tell us a few more interesting things. They are not used that frequently, but since there was a request at the beginning that I should touch upon it, so I'm going to just very quickly tell you what we mean by integral equations and what is the important thing that comes out by looking at the integral. So here is the approach. We have a surface on which there is a hydrodynamic boundary layer growing. It could be any type, doesn't matter. This is delta H over there, and for illustration's sake, I have shown this as a thermal boundary layer which is growing over. On this plate, we have uniform velocity coming in, u infinity, and temperature T infinity, no turbulence. Even if it's turbulence, doesn't matter. And now we set up a control volume quite different from the ones that we had looked at in the differential case. There we took a little element over there. Now we take this big little slice of width delta x and at some distance from the leading edge. So that distance we will call as x. In this, we set up our coordinate system as before. This is x and this vertical direction is y. We take this slice and write the conservation of mass, momentum and energy for this. So the height of this, we will say this is y is equal to capital Y. So this distance normal to the plate is capital Y. And now we'll recognize one thing. On the face AB, there is influx on this side. The fluid is coming in. On face CD, there is outflow there. And we had seen last time that because of the boundary layer, some fluid will leave up, and this we put as an outflow over there. Okay, to quickly, so why this was the case? We could even think of a control volume which is from here to here, here, and then over here. Okay, just this much width. At the inflow, you have u infinity is uniform, so air flow rate will be rho u infinity into the area. Whereas on this face, the velocity at every point is less than u infinity. So if you calculate mass flow rate for small slices here and add them up, the mass flow rate out of this little volume here is less than what came in over here. The balance is what left the boundary layer, and that I mentioned yesterday causes the v component of velocity in boundary layers. So that is what this we are representing in this case. So now we say, well, how can I write mass conservation for this? And we say that m dot AB, we write in integral form now, that this is integral 0 to y rho u dy. One of the reasons why we are calling it as the integral equations. So we can write this for AB, we can write this for CD, we can write this for BC. So we get three expressions there. There is no airflow rate in or out of the plate, so that is not in question. We can then do the same thing for another control volume, A prime, B prime, C, D, which in this case will be this surface. This and this. So this we call the leading edge point as A prime, this as B prime, B and A prime, B prime, B. So this is the control volume we are looking at. We can write the same equation for this. And I'm not going to go into the detailed arithmetic of this. I'll pass it out in the notes. When we do that, we have the displacement of the fluid that takes place from surface B prime B, which is that small element, the element at the top. This is rho u infinity integral 0 to y into 1 minus u upon u infinity integrated over the entire vertical length. Okay, so this is the mass flow rate out of this. Okay, and what this tells you, this is you are integrating 1 minus u over u infinity. This is always less than 1. So you are integrating something else. So that this is the actual mass that is leaving. And this particular thing we can write as rho u infinity into delta. What is the mass left? And here we define delta 1 as integral 0 to infinity, that means all the way out, depending on how thick it may be, u upon u infinity into dy. And this is an important parameter that tells us something about the flow, that by how much has the boundary layer been displaced as far as mass flow rate goes. So this is called the displacement thickness. Okay, so this is one parameter about the boundary layer that tells us something how thick the boundary layer is in that sense. Now we do the same thing with momentum, writing all the equations for A, B, C, D and A prime, B prime and C. Now A prime, B prime and then BA, sorry, BA. We do exactly the same type of an integration, and after you simplify those things, we are left with the fact that you have some momentum leaving the plate, which is 1 into dy. So it is this term is still there, 1 minus u over u infinity multiplied by this, which tells us the momentum part of it, and this expression is defined as another parameter, delta 2. This is called the momentum thickness. And because the way it has been defined, it gives us a very elegant expression for something that we really need to know, which is the local skin friction coefficient, which is 2 d delta 2 by dx. So remember, this is at some location, and at any location along the plate, so this was the plate, at this location we'll get a certain delta 1, which will be delta 1x1. At this point it will be delta 1 evaluated at x2, like that. So these are both functions of x. And this simple expression here tells us that d delta 2 by dx multiplied by 2 is the local skin friction coefficient, which we can then extend to calculate the local shear stress, and from there we can calculate the local drag force, and integrating that we can get the total drag force. So if we know delta 2 as a function of x, we can calculate the drag force on the plate, and that's nice to know that one expression can help us to get all of that. So this is the second important number that comes out for the boundary layer, the momentum thickness. Let's now look at energy. We do the same thing, and we say that q dot double prime at the wall at any location. This, from the same type of analysis, will come out that this is d by dx integral 0 to infinity rho u c into t minus t infinity dy. So T is the fluid temperature normal to the plate, which is a function of y, and that's why T is a function of y, and so is u. So there are two things that we are integrating. So basically we are saying how much is rho u c into T. This C to T is like enthalpy. So rho u h is basically what is the energy flux over that place that we are trying to integrate over the height normal to the plate. So that's what we have here. And then we recognize that we can define a characteristic heat flux in the problem. We did that yesterday also. Let me rewrite. A characteristic heat flux is something that you say, okay, in this problem, the heat flux is of the order of this. It is some number which is a nice indicator of the problem. Beyond that, it doesn't mean too much. This we define as rho, which is given, u infinity is known, C, the wall temperature is known, and the fluid temperature is known. So this is the characteristic heat flux for this problem. And using these two, we now define a new term, that's what we call delta 2. This is defined as integral 0 to infinity u by u infinity. In the numerator, we have t minus t infinity divided by tw minus t infinity integrated over the height. And this delta 2, the capital delta 2, this is another important parameter that comes out. This is called the enthalpy thickness. And this again is really quite elegant in the sense that one of the other way of not dimensionalizing the heat transfer coefficient, the local heat transfer coefficient was based on the local Stanton number. We saw that yesterday. And X tells you that this is the local Stanton number. This is normalizing the local heat transfer coefficient upon parameters which are fixed in the problem, rho c u infinity. And if you look at this expression, this again gives us a very nice, elegant little form, dd2 by dx. So delta 2 again is a function of x, varies along the location downstream of the leading edge, and this differential of delta 2 gives us the local heat transfer coefficient. So very simple, elegant, straightforward answer that comes out. Except that we need to know what this is, and in many experimental situations, this is what we actually do, because we measure point-wise temperatures and velocities, and from there we can then calculate and get the local heat. The last thing to be that comes out of this analysis is delta 4, and this is defined as k tw minus t infinity upon q dot double prime at the wall. This is local wall heat flux. This is k tw minus t infinity, and this is defined as becomes k upon hx. So the relative comparison between k and h, and this is called the conduction thickness. So we have and we'll work a little bit more with this, and we get another very nice, elegant little expression that Nusselt number is x by delta 4, which is we have already defined earlier as hx times x upon. So here we have four things that we have now come up from an integral analysis: delta 1, delta 2, delta 2, and delta 4. Each one of them has a meaning. It is related to something that is happening at the wall, and it gets us very nice, beautiful, simple expressions from which we can calculate Stanton number, Nusselt number, skin friction coefficient, things that are of interest. So it is important to know these, that thicker the delta 1 or the delta 2, what does it mean in terms of the local heat transfer coefficient? That's the thing to know about. These are not non-dimensional numbers. As you can see, it's a Nusselt number case, x upon delta 4. X is units of length, so delta 4 is also units of length. Same thing with here. X is units of length, delta 2 is also unit of length, then Stanton number is a non-dimensional number. So that was a very quick thing about the integral approach to boundary layers. And these are the type of expressions that we get from which we can do a lot of analysis. Problems, this is quite nice to use. Largely, we do use the differential equations to solve a problem. But using the solution of the differential equations, we can then calculate these integral parameters, and they are good to understand what is happening in the problem. So they are not entirely inconsequential right away, even though you may not be using in problem solving, but good to know that these are things that you would like to use when you actually do problem solving. Okay, so now we move on to our next topic and say, how can I get heat transfer rates from cylinder in cross flow? There are many such issues that come up, that we have an object, this is like this pen, it is kept like this, and air is flowing like this, or air is flowing like this, and it's being blown. So we are looking at forced convection. And we are asking what happens to heat transfer on this. Now let's look at some examples first before we get back to doing the modeling. One of the most common things where it will be used is you have a tube on which there is a fluid flowing. So this is like a heat exchanger where there is a second fluid flowing through the tube, but one fluid is flowing across the tube. This is the idea, that you have a tube there, circular, and the fluid comes flowing over it. So a very common application is inside a heat exchanger. That is, the fluid is moving across the tubes. I need to know what is the outside heat transfer coefficient. I need to know the inside heat transfer coefficient, and then I can get the total heat transfer, overall heat transfer coefficient, and then design the equipment. So tube in cross flow, this is a very important and a very basic type of a thing. The second thing is, you could have seen that power lines are hung like this on transmission towers. They are suspended there, and then again there is an insulation, and then this is suspended from the transmission tower at the next point, and these carry power over many kilometers. Now this cable is carrying current, which means that there will be I square R heating. And if the cooling rate is the same, what it means is that the temperature of the cable will increase. When the temperature of the cable increases, it will elongate, thermal expansion. Because of that, the shape of the cable will become like that. The result, the distance between the cable and the ground, this will decrease. So the leakage current from the cable to the earth will start going up, and now we have a problem. On top of that, if there is a lot of pollution in this part, it will make a bad problem even worse. And that could lead to tripping of the power line, because you get an unstable electrical situation and you want to protect all your equipment, and this could lead to a complete grid collapse. But this has happened in some cases. To estimate the cooling of this wire, you'd say that there's a wire which is hanging and have airflow taking over it. How can I estimate the average heat transfer coefficient, and then finally the Q dot per unit length of the wire? So we need to know the heat transfer coefficient on top of that. Yet another example would be that you have a person standing there, and there's a stiff breeze coming on this. It could be that you're in a very cold climate where the temperature of the air is like 10 degrees Celsius. But what will happen is, there is heat transfer taking place from there, and that heat transfer rate, if it were to be done alone without any breeze, that tells us what is called the wind chill factor. So how do I estimate heat transfer rate from a human body? Of course, we are wearing clothes and all of that, but still, as a very first approximation, most of this body can be assumed to be like a cylinder, and it will give us an answer which is like 10, 20, 25% off from the exact value. So it gives you an order of magnitude of what to do, and here we'll say, okay, ignore the fact that the ground is there, I'll just have flow coming onto this, and take this as a cylinder and see what happens. So that's the next assumption we make in analyzing flow over cylinder, that in all these cases we have taken that the cylinder is long, the flow has no other surfaces, which is why it is external flow, and the ends will not have the flow that is happening in the middle part of the cylinder over here will be different from what happens in the end, because here, if you look from the top view, air can even go like that. Center, it is not going to happen. So the end portion somewhat here, this will be slightly different from what happens in the center. A real problem, you'll have to factor this in also, but that makes life much more complex. So what we do is, we say, look, I will ignore the end effects, which could be okay if the length of the cylinder is very much greater than the diameter of the cylinder. If the diameter is, say, 20 millimeters and the length is 50 millimeters, then this is not a good assumption. But if it is 20 millimeters and this length is 100 millimeters or maybe 500 millimeters, then this is a good assumption, that the end effects will have very small impact to what actually happening over the length of the cylinder. Okay, so this is one condition we are doing. We are saying that this is a forced convection problem. It is an external flow, and that oncoming flow is laminar. In the real cases, in this case, it will definitely be the turbulent flow. But we'll look at it differently. We'll start with laminar and see what happens. Well, the way to understand what happens on the cylinder is to understand what happens to the flow over the cylinder, and we will understand that by looking at some pictures. Okay, so this is the first picture that I'm showing. This is flow across a cylinder at very, very low Reynolds number. So this is like 0.01, 0.001 Reynolds number. And what you see here is flow is coming from left to right. This is a real experiment in which we have put something into the flow and taken a photograph at some point of time. And even if we took photograph at another point of time, everything will look the same in this. So in this case, they have put dye, which has been put in water, flowing at 1 millimeter per second across this thing. So what you see is that the flow is coming here, it bends, goes over this, comes down and joins up again. So if you draw a vertical line over there, the left of this and the right of this look almost the mirror images of one another. And that's what happens at very, very low Reynolds number. That's one thing. The second thing you see here, okay, the second thing that we see here is that this streamline is going like this. It is bending very little and then recovering back again. So what it means that flow which is between this streamline and this streamline, as it came over the cylinder, was squeezed in this much only. So what has happened is the flow accelerated along this path. That's the second thing that happened. And then again it decelerated to recover its original velocity. Now let's see what happens in this portion. The streamline came here like this and then almost like turned very sharply and went off. This is not a 90-degree turn, but if it were all the way here, then locally it will go 90 degrees. But this is a fairly sharp bend, then it comes up, recovers, and again it bends and again comes back straight. So there is something happening here, that this is a flow that is going up, and locally at some points here you can say that the flow is actually parallel to the surface of the cylinder. So that gives us a thing that if I know something about the flat plate boundary layer, a little bit of approximation I can get and try to understand what happens over here. And then it goes up over here, the velocity has increased at this point, and then again it comes back and decreases at that. So this is a very low Reynolds number flow. Now let's see what happens as the Reynolds number increases, and here it is increased very slightly, and Reynolds number is 0.16. And again, this is a flow visualization done in an experiment by putting something in it and taking a photograph on it. So what you now see is that at slightly higher Reynolds number, the flow in the front part looks pretty much same what it was there. It has come here, it is bent, it's getting closer to the surface, the streamlines here are getting closer to the surface, and then it is going off back again. But this part is slightly bigger, so that means the wake of the cylinder, this is what is called the back portion of the flow, which is called the wake. This is not symmetric to the front portion. This is something that has begun to happen, and this will continue more pronounced as the Reynolds number increases a little more. Now we are looking at this picture where Reynolds number is 1.54. Very small increase, very small Reynolds number, but see what has happened now. Here the cylinder is there, and the front part it's going like this, but now the back part, the wake has become even bigger, and there is a portion here where the fluid, you can see this fluid has come like this, gone there, and then gone off over there. So what happened over here? Well, the fluid which was here is sort of stagnant fluid over there. Nothing is happening to it. And now we look at this picture. This is at Reynolds number of 9.8. And now we can very clearly see that at the back, this is much bigger, or its size of the wake over here is comparable to the diameter of the cylinder, and the Reynolds number is just about like 10 now. So we are beginning to see something very different happening at the back than what is happening at the front, although up to the top of the cylinder, everything seems to be pretty much the same. Okay, then we look at this picture at the bottom over here. So here we have two pictures. This is at Reynolds number 13, and between 10 and 13 something has happened. Now what you see here is that the flow is coming here and going off that way. But here you see something else, which is that the flow is, whatever fluid was there, it is moving around like this. Some fluid from the outside comes in, some fluid from this goes out, and this is a recirculation region. So two things have happened. You can see this line over here, and the same thing is happening on the bottom also. It is still symmetric. That what has happened here is that this flow which came from here, it did not come down, which it was doing earlier, but it has now moved away from the surface. And the flow here is coming in the opposite direction. So here is a point where flow is coming from this direction here and from this direction over here. At this point, the flow has come to a standstill. This is called a separation point. The flow has separated. This is a separated wake, and this is the wake, which is a separated wake, but it's still attached to the cylinder. So this is happening at Reynolds number 13, and at Reynolds number 26, you see the same thing much more clearly, this wake has become bigger. There's a point here where this is happening like this. The separation point has moved up towards the top of the cylinder. Here the separation point was here. At slightly lower Reynolds number, the separation would have been here. Now it has moved up over here and is slowly moving up over there. So you have separation taking place now. There's a big wake that has happened. Fluid velocities here in general are much smaller than these fluid velocities, and you have a flow very different from what we had earlier. Common feature of all these pictures that I have shown is that if you look at any of these lines, they are all moving in a straight line. Even on the back, the fluid is moving in a nice straight line. There is no randomness in this. If you took pictures at different types, you pretty much get the same picture. Nothing is changing with time. The positions are not changing with time. The fluid is not mixing with one another in this direction. And that tells us that the flow in all these cases is laminar. So you got the Reynolds number 26 and you still have laminar flow. Now, this is a picture at Reynolds number of 24. This is 24. And what I'm showing you is experiments. So you actually make an experiment, put it, take photos, and see how much we are able to learn by looking at the photograph of a flow. And again, the same thing we see here, that you have something you put in the particle and look at the streak lines that happens, and this is what you get. And here you can see that this is moving like this is moving like that, and the separation point has now come up way up over here in the cylinder. It is slowly getting somewhere over there, and it is still a laminar flow everywhere. So you still have an attached wake, and this continues and begins to approach a limit at about, say, 30. You have a much bigger wake, which is now bigger than the size of the diameter of the cylinder. The same thing is happening, and the outside flow is still there. The front part I'm not discussing again, because the front nothing has changed. Front part is pretty much the same as what we had seen in the first picture. This is at Reynolds number 41, and this is another trick that some engineers have used to do this research. What they have done in this case is they have put a dye in the water flow and then seen how the dye gets off from the surface. So here they have coated the cylinder with some material, and then that comes off, and you can see that this is going off like this. Some of it comes back and it is going like this here, and this one is going around like this. So the attached wake is still there at Reynolds number 41, but what we don't see here is that there has been slight oscillations that have started to come in. This picture doesn't show that, and the separation point is at about this point, slightly behind the top of the cylinder. Something else happens as you go to higher Reynolds number, and this is at Reynolds number 2000. The attached wake that we saw has disappeared, and what you see is a time shot where this fluid is come there, this is here, and this is, if you actually see a video, this is no longer a stable flow. This comes out like this and goes there. Then this at the bottom forms a vortex. This is called a vortex, this sort of rotating flow. Then after a while, again another one comes and breaks from here and goes off. Then this from the bottom side it comes. You start having vortices being shed from this, and it is still laminar, and you can see that even though it is mixing, the flow is not having too much of a transverse mixing over there. The separation points you can see now have come almost to the top of the cylinder. The front part is still very much the same what we were expecting earlier. And you go to even higher Reynolds number. This is now Reynolds number 10,000. And what has been done is a layer of smoke or a has been put into airflow. And then you see where that streaks of smoke go. And you see a very different type of a pattern where this is coming in and this fluid bends in there and goes off. This fluid bends in here and comes out. Then this fluid is bending here. And after a while again this will come. So what you are seeing here is that alternately this type of vortices keep going off from this cylinder. This has huge implications for engineering. Not the least one of it, it causes stresses on this. And if you see tall buildings or chimneys, this is something you want to avoid. And if you see that tower in Dubai, which has got something like a funny shape, the reason for doing that is that you break this structure, otherwise the tower will become unstable and collapse. This is called vortex shedding. And we'll see how this affects what happens in heat transfer. Okay, so this is the last picture in the sequence. And there are very few pictures that we will see. This is the case of a cylinder of a Reynolds number 120, which has been heated. on which air is coming in at a lower temperature, and we have used what we have learnt in physics, what is called a Mach-Zehnder interferometer, to see the density gradients. The density gradient is exactly correlated with the temperature. So the dark and bright fringes we see in the interferometer picture are indicators of temperature in this case, and they can actually get quantitative measurement by looking at this picture. This is a very, very difficult picture to take. There are very, very few pictures that you will see, but this is one of the best ones that you can see. And you can see that where is the temperature going? The fluid flow was happening like that. We saw that at Reynolds number 120, it would make a wake which had opened up, that attached wake had disappeared. And that's what you see, that the temperature, if the temperature is also going off like that, you can see these lines one after the other, each represents a particular temperature. And you can see that as you go away, the lines are opening up more and more. Here the lines have opened up even more. Here the lines have, again, they are relatively close. And then again, the lines here are much wider. So what does this picture tell us? That if I take a point here and look at temperature gradient in this direction, my boundary layer thickness is about this much. You can actually measure the boundary layer thickness. Here also it is about the same. Here it has, the lines have got away slightly. Here again the lines have gone away slightly. Here also the lines have gone away slightly. The picture, if it is invariant with time, it tells you it's a laminar flow, which the fluid mechanics also told us was a laminar. So what it's telling us is that the boundary layer thickness is increasing as we go from here, and what the flat plate taught us, that as the boundary layer thickness increases, the heat transfer coefficient decreases. And that's what we would expect to see on this cylinder. And then what do we see? At this point, if I draw a radial line going outwards, the lines which were all so close are now that wide apart. So what it means is that the temperature gradient normal to the surface at this point is very low. That means the local heat transfer coefficient at this point is very less. Again, it recovers a little bit, and here the lines have come back a little closer, but not as close as they were in the front part of the cylinder. So you have a radial, azimuthal distribution of heat transfer coefficient over the cylinder, and this is determined by the flow that was taking place. In this case, as the flow was attached and it moved up to this point, this is what happened. This is the point where the separation was taking place. So the heat transfer coefficient is lowest because now the fluid flow is very small, sometimes in one direction, sometimes in the opposite direction. So that's the type of qualitative information we are able to get. And in this case, we could actually even measure the temperatures and get quantitative information about heat transfer coefficient. Okay, so this picture, and if we extend that to all the other pictures that we saw, this will give us a total picture of what happens locally over a cylinder. And then if we do an area weighted average, then we can calculate what is the average heat transfer coefficient over the cylinder. And that will be equated with Q is equal to HA delta T. So let's now see what happens and try to see what type of categories of flows that we can have for cylinder in cross flow. And the first one we have is that first picture that we saw, where Reynolds number, where the flow was completely symmetric and attached. So it went off like that and joined up there. From the bottom it went up there, it went up there, and it went up there. These streamlines here were squeezed in compared to this. So the heat transfer coefficient here is going to be better. Here it's going to be something, and then at the back it will recover and be almost symmetric, but it will not be uniform all over the place. So this flow has no separation and it is completely laminar. And the thing is that across this it is symmetric. So that is one regime, Reynolds number less than 1. And I'm showing different regimes to show what the flow is. And based on these regimes, we have a different type of correlation for every one of them. All the correlations will have this form, that Nu average for the cylinder based on the diameter of the cylinder. This is equal to some constant times Reynolds number to some power multiplied by Prandtl number to some power. These powers, this constant, which will be say A here, and this is a B, and this is C. A, B, C will depend on what is the regime of Reynolds number that we are looking at. So that's the reason for looking at it this way. These numbers I will put out in the notes, or you can pick up in any textbook. The second regime we looked at was attached wake. On the attached wake, what happened was that here we had a recirculation region coming in, and this flow was going off from that time. So this is a laminar attached wake where first the separation started over there and then it started coming back over there. Okay, so this is the second regime that we have. Third regime that we have is 40 to 1000, in which we had laminar separation with vortex shading. So what we have is that this thing came up and now this was happening like this, and from this side it was happening like this. So there these things are phased apart, once from this side, once from this side. The flow was still laminar and we had a separated vortex shading which was laminar. So this continued till about 1000, and of course there was a separation somewhere over there. And then you have 1000 to 2 into 10 to the power 5. You have laminar plus separation happening. So you have this thing there, and then the flow is going very deeply inside each other and forming various shapes, and it is oscillating. So this has now become unsteady. And the last one, which is after 2 to the power 2 into 10 to the power 5, is that you have laminar plus a turbulent separation. And what happens here is this boundary layer begins to grow first as a laminar boundary layer. Then at some point it becomes a turbulent boundary layer which remains attached for some time, and then you have completely open turbulent wake coming in. So this is the starts as a laminar one, becomes turbulent and separates, and this is what you get. So for these 5 regions, there's 2 things that happen. One, that the local heat transfer coefficient depends on the angular position. So if this is the angular position, we call this angle theta. We get some numbers over there, and based on that, the Nusselt number, the local Nusselt number, can also be obtained. And second, what I had already just mentioned, that based on the diameter, the average heat transfer coefficient for the entire cylinder, irrespective of what happens at local points, this can be obtained as a function of Reynolds number based on diameter and Prandtl number. So some exponent there, some exponent there, and a pre-exponent over there. Okay. So this is the type of thing that we have. And after this, the approach to problem solving is pretty much similar to what we have for flat plate boundary. So with that, we will leave cylinders in cross flow and move on to very quickly to a small application which is very important for all types of heat exchangers. The pictures I showed day before yesterday, I showed you some heaters. So there were hundreds and thousands of tubes very closely packed to one another inside a shell over which the fluid is flowing. How do I compute or predict the average heat transfer coefficient for the entire bank? Now that's the thing. So H bar for the bank. Bank means the whole bunch of tubes. What we learned just now was a single tube. But now what happens is in a tube bank, you have at least 2 arrangements are possible. One is like this, where the flow is left to right and all the tubes are aligned with one another. The second is where these tubes are there and these are staggered from this. So this generates very different types of flows. That here you have a flow which is happening like that, and here it goes like this. Whereas here this will go like that, and then it gets over there, and then it again comes there, and something like this will happen. The important thing that happens here is that the wake produced by this tube influences the heat transfer on the second tube. So this will have high heat because the wake is there. The ambient fluid is not able to come close to this. So we know by understanding what we have learned so far, this tube will have less heat transfer than this tube. This will have even less than this, then less than this. So just putting more and more tubes one behind the other does not necessarily give us the type of advantage that we are looking for. That problem is a little less in the case of staggered tubes. So we decide that how many tubes are there in a bank, what is the number of their depth, and what is the arrangement this way and the arrangement that way, number of tubes. And then people have done lots of experiments, and these days now lot more computer simulations are also coming up. From there, again, they have developed some correlations, which will be like average Nusselt number for a particular type of a tube bank is something based on Reynolds number based on tube diameter, or now the parameters that come into the problem is this spacing and this spacing, or in this case you have this spacing and this spacing. So based on these combinations, you'll get different expressions for Reynolds number. There are whole books dedicated to just this topic because they are so important for all types of heat exchangers. One can look up those books to get these things. It is right now we are only going to say that look, this exists, this is the reason, the way it is done, and this is how we can use these results. So that's a little takeoff from the cylinder in cross flow. So individually, each tube you can theoretically say is a tube in cross flow, but actually it is not, because this is getting influenced by the wake of the tube in front of it. Right. So that was tube banks. You can look up the book and also look up things on the last geometry, which is the simplest of the geometries, which is flow over a sphere. The sphere with diameter is d, and what happens when you have airflow coming onto the cylinder? U infinity and T infinity. What happens? We will not go into the details of it, but there are some aspects of this where the regimes of flow are somewhat similar to what we have just looked at for cylinders. And again, you'll get average Nusselt number based on the sphere diameter to be a function of some constant multiplied by Reynolds number based on the diameter of the sphere to some exponent multiplied by Prandtl number to some other exponent. So this is given for different ranges of Reynolds number and for different Prandtl numbers. So you have to pick up the right combination, get these constants, and solve the equation. That we will leave that over here. We'll now go to the last topic, which is a little more involved than the cylinder and sphere problem, and that is internal flow. And what we mean by internal flow is how a fluid flows into a tube or a duct or a pipe. And what is the question we are asking is, how can I understand the heat transfer between the wall and this fluid? In some sense, how can I get the local heat transfer coefficient, and how can I get the average heat transfer coefficient for the tube? Before we get there, we look at the word internal flow. And this is in contrast to what we had looked at up till now, whether it was sphere, cylinder, or flat plate, which were all external flows. And what we had classified it in the beginning is that in external flow, the object is there. In this case, there could be a flat plate, a cylinder, or a sphere, or anything else. The fluid is all around it, and for long distances on any side, there are no surfaces. Far away from the object, the free stream conditions prevail. So if this was U infinity, T infinity, here also it will be U infinity, T infinity. There are no other surfaces in the problem. In contrast, internal flow, and this could not just be a tube, it could be, say, the flow inside a room due to a fan that is going on. Here, the fluid which is moving, say, inside the tube, flow here, the fluid is completely enclosed by the surface. From the fluid mechanics standpoint, what it means is that in this case, in external flows, there is a region around the object, and that is what we call the boundary layer and then the wake. This is the region that is affected by the presence of the object. The rest of the fluid is not affected by the presence of the object. In this case, every element of fluid inside this, every little fluid particle or fluid small volume, every one of that practically, except for a small portion in the beginning, sees the effect of the plate or the surface. So it could be a tube or a duct or two very large flat ducts. It will see the impact of the surface at all times. And this completely changes the way this flow has to be analyzed compared to external. So what we do here is, first, as you have learned in fluid mechanics, if the fluid enters with a uniform velocity, and that is another big if there, so let's spend some time on that if. If you just have a tube like this and flow, say, being sucked inside this, and this is a very large space there, then at this plane your air will go like this, some air will come like this, the central part, the air will come like this air will come like this fluid will come like this. At this plane, the velocity vectors will not be uniform. So here you will have this velocity vector, including if I am showing the magnitude also. The flow is neither uniform nor is the magnitude same all over the place. This is what happens in this, which would be called a sudden entry or an abrupt entry. How do we avoid this? Is to make the entrance region very nice and smooth. So what we say is, I'll have this tube, and inside, over before that, we'll put a nice bell-shaped thing, and then suck the air or the fluid through this. So what will happen is, this air will be non-uniform at that point. As it comes in at this point, everywhere the velocity will be the same. So this is what we say is where the tube begins, and this is X. So this is what we may call, this particular shape would be a bell mouth, and it produces a beautiful, well-behaved flow at the entrance of the tube. But then why do we worry about this? Because as you saw the photographs of those heat exchangers, none of them had this. Everybody had this. Because this means you got to put additional material. The whole thing becomes a little more complicated, more expensive. You say, look, I can't be worried too much about it. I just go with this and make some correction factor in my design so that the objective is realized. This is easy to manufacture, so we'll live with this. So this is what you see in a real case. It may not even be that symmetric, because if you have tubes over there, as you saw in that heat exchanger, and the fluid enters from this side. It comes in from here and is then distributed into the tubes. You would have even more asymmetry in the flow than what we have shown over here. Not to mention the fact that if this is not designed properly, there will be some tube where you have more flow taking place, some tube where there may be less flow taking place. So the assumption that all tubes have the same flow may not even be true. And that's what you have to worry when you look at tube banks, and you have to design of this and this particular shape that distributes this fluid into this. This in engineering terms is called a header. So we'll not worry about that, but important point is this, that in the analysis that we are going to look at, we are going to look at this part, that the entry, this is a smooth entry. And with that, we now start asking some basic parameters and questions about this flow. First, how do I define the mean velocity in this? And here we say this is the total mass flux, or the volumetric flux, divided by the area of cross section of this duct. So this is very, very general. It could be, the duct could be triangular, it could be rectangular, it could be circular, it could be any other shape. And it could even be a duct like that, which is what you see in automotive radiators these days. So that is the definition of the mean velocity. It does not mean that the velocity at the center is this or this anywhere else is this. The actual velocity at any point here, it could all be different than what we have. The thing is that even though as you go in this and you have learned in fluid mechanics, V is a function of R, V is not a function of R. this is constant for a given tube. It's a constant. It's a number only, and the distribution is not something that we are worried about. The second thing you have learned in fluid mechanics is the definition of the hydraulic diameter, which is 4 times the wetted area divided by the perimeter. Okay, so the area of cross section divided by the wetted perimeter. So P is the, if you take any slice over there, what is the area through which the fluid flows? That is your AC. P is the point area of the line of contact between that cross section and the surface. And that is the basis on which we define the hydraulic diameter. And in general, the Reynolds number for these cases will be based on the hydraulic diameter as dHV upon mu, the kinematic viscosity. For circular tube, life becomes easy. Hydraulic diameter is same as the diameter of the tube. Now let's see what we have learned in flat plate boundary layers. Can we extend that in some way to what happens inside a tube? So we say that this is where the tube begins, and first we'll quickly draw the hydrodynamics of it. And an important thing is this Reynolds number based on tube diameter if it is less than 2300. So case 1, we look at this thing. So what happens here? Locally, in this small region, if you take a small slice, you can say that this little part of the tube behaves like it's a flat plate on which the fluid is coming, and so the boundary layer growth will be somewhat similar to what the flat plate boundary layer growth was. But it is circular, so it is having its effect. So what happens as this boundary layer grows? We learnt in the flat plate boundary layer that there is mass flux normal to the surface. And this is going to happen over the entire periphery. So fluid is being pushed by the tubes of the wall towards the center. What does that mean? Is that if at this point the boundary layer thickness is this much, then here you have this shape, same with all over the place here. But in the center, where the velocity was this much, this fluid which got pushed in the center has now got to go out of this. Continuity requires that. So the center line velocity in this case will now increase. So you have this portion where the fluid has accelerated because the boundary layers are building up on that side. So here the velocities have decreased, here it is decreased all along the periphery, and in the center, your still velocity is going up. There is no shear yet in this part. As we go a little down further, the boundary layer begins to get thicker, but now the effect of the free stream begins to come in, and we can only get very rough qualitative idea from the flat plate boundary layer that we thought would be in the beginning. So here now the boundary layer has become thicker, and the flow in the center has accelerated, and you have now a velocity profile with a small flat portion, and it becomes like this. These 2 points will join up, and you will not have any flat profile in the tube at all. So the velocity profile becomes like this, and that you probably have learned in fluid mechanics that this is a parabolic profile, and that is the case when it is this, which means that the flow everywhere here is laminar. Once flow has become like this, from this point onwards, this profile does not change. And this is what we call a fully developed velocity profile. So here, V at any location is only a function of R, and dV R by dx, which is in the actual direction, is 0. That's what we call a fully developed profile. And this portion of the tube, where the profile was changing, this is what is called the hydrodynamic entry region, and this length is the entrance length, LE you can call it, that it requires, so after a smooth entry, you need so much distance for the flow to become fully developed. So this is an important thing that comes up in this problem. So we have an entrance region and then a fully developed profile. If the entry were not smooth, these profiles will be different, but after a while, this profile will settle. So that will require some other length for all of that to happen. So this is what happens in this case. And now we say, well, what will happen if Reynolds number is greater than 2300? We go back and say, no, this little portion here, this behaves like the flat plate boundary layer. So it will start growing like a laminar boundary layer profile, but very quickly become jagged and become a turbulent boundary layer. So very short region, locally it will reach certain Reynolds number where the flow will transit from laminar to turbulent. You have a laminar boundary layer growing all over the circumference. These boundary layers grow much faster, and at some point, say somewhere here, these boundary layers will merge, and you get at this point a velocity profile which is somewhat like that, a mean velocity profile which is like this. So for this particular type of situation, where now we are looking at RED greater than 2300, this is the entrance region. This was for the laminar case. This is entrance region for the turbulent case. And after that, this profile does not change, it remains constant. And when you say laminar profile, it doesn't mean, like in this case, if you take a photograph, as we saw in those pictures, at one point you get something, second point you get another picture, but it's the same, third point you get the same. Here you get slightly different things because the turbulent flow, sometimes it will be like this, sometimes it will be somewhere there, but our average of that is what we will get. So this is now the fully developed turbulent profile. And that was the fully developed laminar profile. Now what happens is the length required, the entrance length for development of the laminar condition is much greater than that for a turbulent profile. So that in many ways for engineering is actually quite easy because this part does not influence us too much. And the importance of this is we can go back to the flat plate boundary layer and say, well, what do these boundary layer growths tell us? Simply that as long as the boundary layer thickness is small, heat transfer coefficients are high. So in the entrance part of the tube, heat transfer coefficients will be much higher, whereas in this part, heat transfer coefficients will be relatively less. So a good guesswork is that here it is of the order of 10 times the diameter for turbulent entrance length, whereas here it could be anything up to 100 times the diameter of the tube for the flow to become fully developed. So that is one thing. The second thing is now we impose a heat transfer condition on this tube. And like we had looked at the flat plate, we have two options. One, the wall is at constant temperature. That means you have example like a thermal power plant condenser, where inside you have cooling water is flowing, outside steam is condensing. Steam is condensing means that its temperature and pressure are going to remain the same. So the temperature is constant. The wall being a very good conductor, you can say that the temperature of the wall is almost constant. That is an isothermal wall for the case of a tube. The second is the case where, say, you have a tube going in and this is wrapped up by an electric heater and you have constant heat flux case. You'll also have a similar condition if this tube were getting solar radiation. Solar radiation also produces the same boundary condition of a constant heat flux in the wall. So you have two conditions that we need to look at, and that's what we will do now. We'll develop one important thing, and then that's where I think we'll run out of time, which is that in the isothermal case, let's see what happens to the temperature profile. We assume that temperature at the inlet was T in and it was uniform. So temperature here everywhere was this much. And I'm saying again that temperature is being shown by arrow only to show the magnitude, not the direction. It's a scalar. And TW, let's say, is greater than T in. Thermodynamics tells us that the tube is very, very long and infinitely long, and you keep blowing it. This fluid will finally everywhere come to this T wall temperature, and that's the maximum you can get. Okay, so now let's see what happens to the temperature profile as the flow goes through this. The same thing, a local thermal boundary layer will begin to develop over there. And so at this point, if we draw the temperature profile at these different points, you'll have some region here. At the wall, no slip condition means that the temperature is the same as the temperature of the wall. In the center, the effect has not gone. So the middle part, the temperature will be same as T in, whereas at the wall, it is TW, and in between, the temperature has increased. So you get a temperature profile which is flat in the middle and it's gone like that. This portion is where the heating effect has been experienced. A little further down, this heating effect will go further. So the flat portion will now be only to a smaller extent, and TW remains the same at the wall. So you will see this and this. So a small flat portion. And after a while, this flat portion will be the first point where the flat portion will disappear. So it was here, this is the wall, and you'll have a profile like this. Wall temperature at the edge, and at the center, it is still T in. Now the question is, what happens as it goes further? In the case of velocity, we saw that the profile did not change. Now let's see what happens in this case. Because more energy is coming in, all of this will begin to get heated up. And so what we will have here is a temperature profile which is like that, the wall temperature remaining the same, but the center temperature will now begin to increase. And if it is infinitely long, slowly this curvature will become less and less, and the profile will become flatter and flatter. So what this entire picture tells us is that unlike the velocity profile, the temperature profile never becomes constant. It keeps changing along the length of the tube. So the definition of what is a fully developed thermal boundary layer, that is the question. So here we say, well, what is the meaning of a fully developed thermal flow or a fully developed temperature profile? Question is, does it even occur? Since absolute temperature is not changing, it's not happening anywhere. So we'll come back to it in a minute. Now let's look at the second case of constant heat flux condition. Okay, and so what it means is that this is the central line of the tube, and we got a constant temperature coming in over here. And what this thing tells us is that Q dot double prime at the wall at any location is constant. So what will happen is that the gradients will have to adjust depending on the temperature difference. So initially, because of that, you'll have a very sharp temperature rise over there, and everywhere else, the temperature profile is still the same. And then this temperature, TW, is now determined by something that how much this is equal to the local heat transfer coefficient multiplied by the wall temperature at that point minus some fluid temperature which we have not yet defined. Since this is constant, and if this doesn't change too much, this has to remain constant. So what is happening here is that the slope here will keep on getting bigger and bigger. That means here the wall temperature will keep getting more as the fluid also gets heated up, so that this is almost constant. So here you will get a temperature profile which is maybe something like that. The temperature at the wall has increased. When you go further, the temperature of the wall will further increase. So does the fluid temperature, and you'll get a profile like that. Since the fluid is getting hotter, the heat flux is the same. The only way things can remain same if delta T is about constant, which means that the wall should keep getting hotter and hotter. And this is a problem. That as the wall keeps getting hotter and hotter, whether it's a tube inside or it's a tube which is generating heat through which this thing is flowing, like happens in a nuclear reactor, you could have temperatures increasing quite a bit here. So the temperature profile here also, like the first case, does it become a fully developed thermal temperature profile, and is it invariant? This is the question we are asking. And fortunately for us, if you look at the fully developed portion, and of course here what we have done is we are looking at the case where the hydrodynamic boundary layer is developing. From this point, at the same point, the thermal boundary layer is also developing in both cases. So both boundary layers are developing simultaneously. a reasonably good approximation in many applications. The one is good to start off with. There are other variants that we need to worry right now. So let's see what happens to the temperature profile and how we can analyze this problem. So here is what happens. We define the mean temperature as a point that if any location on the pipe, we take the flux, so that's the pipe or the duct, whatever it may be. We take one location, we see what is the cross-section area there, and at every point in this, we say, I know what is U and what is T. And we define a mean temperature, or also it's called the mixed mean temperature. The mean or the mixed mean temperature. The definition is that this is the total energy flux that is taking place through this, which is U into T into that small elemental area integrated over the area. So this is a area integral. So you took a small element on this and said that U and T on this little elemental area dAc is this much. I'll integrate it over the entire surface, and that is what this integral is all about. This tells us the total, in a way, the energy flux through the surface, and that will divide by the mass flux through the surface. Your density gets cancelled, which is AC into V. V was the mean velocity that we have just defined. So this is energy flux divided by the mass flux, and that gives us a representative temperature, which is the mixed mean temperature or the mean temperature of the. Okay, so this is an important definition. Like we had the mean velocity in the hydrodynamic part, here we have mixed mean temperature at any location as the number that we get. So at any location in the pipe, in either of these cases that we looked at, we can say that any location I can define Tm, which is a function of x, and we know as heating takes place, Tm will keep on increasing. If it is cooling, it will keep decreasing. And we say what is the heat transfer over a certain length? It will be m dot Cp into T in minus Tm at the exit at that point. So we even get the bulk energy balance very nice. And that is independent of whether it was a constant heat flux heating or a constant wall condition. Okay, so that is one definition. And for a circular tube, we can express it in terms of R, that the mean temperature at any x is 2 upon V into R squared, integral 0 to R, U xr Txr dr. It's the same thing expressed for a circular tube. And now we define a non-dimensional temperature, which is Tx star, defined as the wall temperature minus the temperature at that x and r location. That means at any point in this surface or anywhere in this tube or the duct, if you take any point and which is coordinates are x, which is from the entrance point, and r, which is the radial coordinate, then the temperature at this point, we will convert it into a non-dimensional temperature by saying this is Tw at that point minus Txr upon Twx minus Tmx. So this is an important definition of non-dimensional temperature for an internal flow. Now look at this expression. Something striking comes out. Why is Tw a function of x? Now that will happen if it is a isothermal wall. That means it is a temperature case, constant case. Then everywhere Twx is no longer a function of x and it is a constant at Tw. So this becomes a constant. What about the mixed mean temperature? As you go along the line, this is changing with a function of x. We just saw that. So this remains as a function of x. This is, of course, the local temperature as a function of x and r. So this is what we define based on local parameters and not on global parameters. For the case of H condition, which is the iso heat flux case, as we saw in this case, the wall temperature will keep on increasing because it's an electric heater or say a radiation heater. So here Tw is a function of x and it changes. Okay, so this is an important thing. Why? We are non-dimensionalizing it in such a way that we have both x and r coming explicitly into the expression. So if I have to normalize the temperature in this plane, I have to get Twx at this point and Tmx for this area and normalize it on that. At another location there, We have to get TWX at this point, mixed mean temperature for this area, and then we normalize it on that temperature. So that is what this temperature definition is. And now this can be defined for both cases, either a fully developed velocity profile, laminar or turbulent, and also a temperature profile that is put on it, T or. And the nice thing is, and I'm skipping all the algebra over here, is that we can say that the temperature profile is fully developed when the non-dimensional temperature that we have defined is independent of x, but it remains a function of r. Okay, so if dt star by del x is equal to 0, we say that the temperature profile is fully developed. And if that happens, it means that throughout the tube at all times, at any location x and r, the temperature will keep changing along the length of the tube. So it is not like the hydrodynamic fully developed velocity profile where it is independent of the position. Here the absolute temperature is dependent on the position, but the non-dimensional temperature is independent of the exchange. That's the difference in this definition. And you can prove that either case, the isothermal case or the isoflux case, this condition is consistent with heat transfer, and this is a good way to define it. Now what are we left with? We have that at the wall heat flux is the local heat transfer coefficient into wall temperature at that point minus the mean temperature at that. So we are defining Hx on the basis of the mean temperature at any location. Even though this itself is a function of temperature in both isothermal and isoheat flux case, this is a function of the actual position in constant heat flux case, but not in the isothermal wall case. So that's an important thing in which it tells us that we have a small element of this tube, a slice if we have taken it, then the local heat flux at this wall is q dot w prime wx. This is the local heat transfer coefficient for this slice multiplied by the wall temperature at that point. So you have Tw of x coming here, and for this entire element, the mixed mean temperature, which is Tm, which is a function of x, which is at this location. That's what this expression tells us. And this is equal to minus k dt by dr at r equal to r. So this is a fundamental equation which will always be true. There is no running away from this. So what we have is that when you substitute this, you get dt star by dr equal to hx by k, and we can see this now that hx is constant for fully developed temperature profile. It is no longer a function of the length from the entrance. So this is now quite different, and this depends because Hx is defined in this particular way. In the flat plate external boundary layer, we had defined this as Tw minus T infinity, which was always a constant. And so we said that as the boundary layer thickened, the heat transfer coefficient decreased. In this case, because the way we have defined the Hx and the temperature difference, we get this very interesting thing that if you do the complete algebra and solve it, that Hx dt star by dt, which is the heat transfer at the wall, is Hx by k, which is constant. So what it means is that we now have two portions. The entrance portion, where the velocity temperature profile is not fully developed. So in that case, H is not going to follow this trend, and if you have to plot that along the length of the tube, so this is the entrance region. What it is tells us that if you are plotting on this axis H, and this is x equal to 0, then here the flat plate boundary layer tells us that at the entrance the heat transfer coefficient is very high. As the boundary layer builds up, it will decrease. So in here it will follow that thing. But what this other expression has told us that after a while, when the flow has become fully developed, say at this point, H is constant. This is a nice thing to know. Okay, so if we neglect this portion, the solution of a problem is very easy. That you say that in this case, Nu, average Nusselt number, is constant. In one case it is 3.66, in another case it is 4 point something. and you can look up the book and say, okay, I'm sure that the entrance region is gone, it is not important, and so I can apply this thing. You can use that provided this length is small compared to the total length of the tube. If this region, entrance region, is of the order of say 30 millimeters, or say 300 millimeters, and the length of the tube is 10 meters, then you can say this is very small. This portion where there is a higher heat transfer rate is small. I can ignite the average heat transfer coefficient, which will be the average over the entire length, will not be very strongly affected by a small length where the heat transfer coefficient is higher. So I can neglect this and just go with these numbers. So that's one nice thing that comes out. But if the entrance region is 300 mm and the tube length is 600 mm, then we have a problem. Part of the length Nusselt number is constant, the other part it is not constant. So we now have to do an averaging, length averaging. So hx into dx in some form, going from 0 to L, 1 upon L. This will give us the average heat transfer coefficient of the average Nusselt number. And what does it tell us? That this case, the average heat transfer coefficient for the 600 mm long tube will be slightly greater than for the 10-meter long tube. And so, okay, if that is the case, if I make the tube very small, instead of 300 mm, the tube is only, say, 150 mm, then what is the heat transfer coefficient? Then you say, look, it doesn't even get time to get a fully developed temperature profile to form. So we are in this region only, here to here. And now I have to use relations for this to get the average heat transfer value. And this is a little more complicated because here you have h as a function of x also coming in. There are some relations in literature, we can pull that out and do it. But the fact then remains is that the average heat transfer coefficient with the 150 mm tube is going to be average heat transfer for the 300 mm tube and greater than for the 10-meter long tube. So it tells you that if possible, instead of making a long tube, maybe break it up and make it into smaller length tubes that are in parallel, provided the mass flow rate through each tube is the same. That may not always be the case. So if you do that, you now have the advantage of heat transfer coefficient increasing, and so your total heat transfer area requirement goes down. That's the type of trade-off people do, and finally you get an engineered product like, say, a radiator or the evaporator or the condenser of an air conditioner, where there's a certain length of tubes, and then you have calculated what will be the heat transfer on it. It's not necessary that the ducts. So what we have come to point is that we have been able to get what happens inside a tube. By and large, this will happen in most shapes. And if we have to get what is the value of the Nusselt number for a developed temperature profile, we can look up the literature and get that. That is one case. If it is not, and it is partly developing, partly developed, that is the second case. And third case, when you never have a fully developed temperature profile, then what do we get? So these three things, you get different types of correlations. All in the first case, Nu will be constant. It does not depend on, it only depends on the diameter of the tube or the hydraulic diameter of the tube. In the second case, Nusselt number will also be a function of x, and here it will also be strongly a function of x. So that's what the analysis is. We pick up those correlations, get value of h, and do the rest of the calculations. Okay, the last remaining is, how do I do the cleat analysis of the tube? And the reason is this. The problem that we have been looking at is that we have a tube, there is an entrance portion somewhere, and an exit. So here it enters, here it exits, and here is some heat transfer thing that is happening on this. Okay, I'll come back. Now we got H bar for the tube, and so we say that Q dot from the wall, or Q dot in this tube from wall to the fluid or fluid to the wall, this is H bar into area of the tube. Area of the tube is pi d into its length multiplied by some temperature difference, which is somewhere a T wall or a T wall X minus T mean something. But this, in a global sense, if you look at thermodynamics of all of this, can be also equated to m dot Cp into T out minus T in, where T out is the mean temperature at the exit at length L. So how do we get what sort of a temperature do we use over here? And that is where there is a problem. Wall temperature is changing with length, say for constant heat flux case. Mean temperature is always changing over this. So if I have to apply H, what is the corresponding delta T on which we apply H? So this has a problem over here. So this term gets replaced by something we will call delta T Lm, a sort of a logarithmic mean temperature difference. And this is defined as delta T Lm. In heat transfer analysis, you will come across this as LMTD. The definition is exactly the same. And this is defined as delta T at the outlet minus delta T at the inlet over Ln delta T out minus delta T in, where delta T out is T wall at the T wall minus T mean temperature at the outlet, or the wall outlet temperature, and T in, delta T in is T wall minus T mean at the inlet, which would be in. So that's the temperature difference to use with H for the whole plate. That's one thing. And if you want to know what is the mean temperature difference along the length of the plate, which is that this is our X here. How does X, if I have to plot the mean temperature as a function of X, what do I get? For that the expression, we can derive the whole thing, and the final expression is written here, that the mean temperature at any location is wall temperature minus Tw minus Tn into exponential this parameter h P upon m dot C multiplied by the x. So it is exponentially changing temperature along the length. All of this has been done for the constant temperature wall. Okay. For the constant heat flux case, you can do that separately. I'm not going to go into the details of the point, but the idea was that to use H for the entire tube, we need a logarithmic temperature difference and not just a delta T. Okay. So on that point, we look at this last thing, which is for the constant heat flux case. The Q dot double prime at the wall is rho C VR, V is the mean velocity, by 2 into the gradient of the mean temperature with X. In the fully developed case, this is going to be constant. Temperature profile is fully developed. What it tells us in the constant heat flux case, that dTm by dx is constant. That means the temperature, say if you are electrically heating it, and this is x, length of the plate, and this side we put Tm, it is increasing all the time. And because this is T wall at x minus T mean at x, it means that both are increasing by the similar amount, and so the wall is getting hotter and hotter, and that could cause a problem to an engineer, because at some point it could damage the tube. So this is what happens in a constant heat flux case. The dTm by dx is constant. The temperature of the mean temperature of the fluid keeps increasing, the wall temperature also keeps increasing, and the temperature difference. Okay, so with that we have covered all the basics of what we need to know about heat transfer inside tubes. And it doesn't matter whether tube surface was like this or tube surface is triangular, as you will see in some of the radiators in a car, or it could be, tube could be like this. This is also what you see in a radiator. This could be in a air. So these are all types of shapes which are there. An air conditioning duct, for instance, would be that big. Some could be much bigger, say a thing in which solar energy is heating up a surface and air is being blown on it. That could be this. So it doesn't matter what the shapes are. We have a broad basis of scientifically understanding these problems. That is where we'll stop and we'll now take questions. Okay, the question is boundary layer separation condition is same for both thermal and hydraulic condition? Okay, so if the question is this, that if you have a flow past, say, a cylinder, and you have separation taking place, say, around 90 degrees in the case of laminar flow, it's about 120 degrees if the flow has become turbulent. So flow has come there and it goes off like that. So here the flow is coming this way. So this is the separation point. So this separation streamline. So what it means is that at this point for separation, the local skin friction coefficient is 0. Because here, normal to this thing, du dy has become 0, and this also happens for a flat plate. So in the fluid flow case, this is what is happening, but in the thermal case, this is not going to be 0. It is going to remain finite. So you would still have some dt dy, which in this case is going to be very large, because the fluid is not taking away its energy, it is only taking adjust to conduction. So it will at the same point cause a very low heat transfer coefficient at that point. Yes. So it will, in that sense, Prandtl number is close to 1, which is say water and air, which is what we're looking at. This will happen that where the hydrodynamic separation takes place, you will experience a very low heat transfer coefficient at that point. Okay. Yeah. Any other questions? Okay. I forgot to mention one thing about internal flows. In external flows, we said that we evaluate fluid properties at T film. I gave the example of the isothermal wall. For the iso heat flux wall, it will be some sort of a mean temperature of the wall, which is a half mean temperature of the wall, TW wall, plus T infinity. In internal flows, this will be some sort of a mean of the inlet outlet wall temperatures. So T in minus T mean out averaged with the wall temperature. These are important considerations, and they often make life much more miserable, because in some problems, as I mentioned, we don't know the temperatures explicitly to begin with, so how do we even get the answer? So the problem can be involved, and some of these problems do take a bit of time to get done. Another question? What is the effect of flow separation at wake? So I'll just go to the picture and answer this. So this is a question which says, okay, you can look at this picture only. Okay, so this is result number 120, and we had looked at something where this is happening. So let's see one of the earlier pictures, which is the closest result number we get on that. So here there is 28, and this is say 40. So okay, let's say 40. So this is what is happening. So what you saw here is that there is separation taking place over here, and this is the wake which is being formed. So what has happened here is that the wake remains attached in this case, whereas in the larger Reynolds number, which is what we are looking at here, inertia of the fluid is so much that it does not allow the wake to remain attached, and it alternately comes down and then moves like this, and then moves off there like that. So the wake is now not attached. The result is that at the back, you have a lot of fluid which is say partially getting swept away at some point, and then it remains stagnant for some time, then again from here. So the wake causes alternatingly higher and lower heat transfer coefficients with time as the vortex keeps shedding. So this is what the separating wake does. In this case, you can see that the laminar separation has taken place here, and this entire region, there is very low fluid flow rate, which means that heat transfer coefficients here are going to be rather small. And that's what you would expect, that if you are standing in, say, very cold breeze coming towards you, you stand facing the breeze, you feel very cold on the face, or the hand, if it is there, the front part of the hand feels a lot more heat transfer than the back part of the hand. So that is what the weight does to the heat transfer coefficient. And what the separation does, well, the separation and the weight, two things are happening as you are seeing here. In one case, it has separated but remained attached. In the second case, the separation has taken place and the wake is no longer an attached wake. So separation does two things. The only thing that separation point is affected by is, say you have a flow, you have a cylinder, flow coming here. Separation will take place at about 90 degrees if the flow entirely is laminar. Whereas if the flow were turbulent, then the separation point would be somewhere here. So the flow will come here and then go there. So that's what the wake in the separated case will be a little smaller than in the laminar case. If there are any more questions, you can post it on the web, on the forum. I will take those up and I'll put out the assignments and the notes are there. If you have any doubts or queries on that, feel free to post it on the forum. Okay, thank you.